Howdy everyone, welcome to our research presentation, Elevation Surveying, In Situ versus Lab Data Collection. The researchers for this presentation were Georgina, Paige, Miko, Nate, and Kristen. In today's society, there exists a plethora of tools in order to collect data, whether it be acquired in the field or in the lab. With the advent of systems such as Google Earth, it seems possible to acquire field data without ever leaving the lab. The question presented in this study is whether or not these systems, Google Earth, provide as reliable or more reliable data than in situ data. The study was conducted by sending researchers into the field and collecting X, Y, and Z elevation points, and then collecting points on Google Earth. These points were then used to create a raster image of the surveyed area denoting its elevation profile. Through data analysis and data visualization, it became clear that in situ data is far superior to data acquired in a lab.
Technology's role in science is accelerating at a rapid pace, and some data can be gathered without even stepping foot into the field. And with technology increasing, it's really good to find out what works, because there's a lot of technology that just doesn't work. With that being said, a lot of the technology that does work can be really expensive. With that being said, is it actually possible to accurately survey elevation without collecting in situ data? And if so, is there a correlation between how data is collected in the field and the accuracy of the data being collected?
In order to conduct this project, a Garmin GPS Map 78, a handheld GPS device, was used to record points around the site. The site, Wolfpen Creek Amphitheater, was chosen because of the hills and slopes found there that are uncommon in most of the rest of the city. Two different methods were used to collect data around Wolfpen Creek: systematic and random. The systematic method ensured full coverage of the park by collecting data after a predetermined amount of paces. To collect data, a person had to travel up and down these horizontal intervals, or lanes, and collect waypoints. Once a person reached the end of a horizontal lane, they would take 2 paces to the right, facing the front of the park, and resume taking waypoints in the vertical direction. These intervals created a grid across the control area in which the waypoints were equidistant coordinates. For collecting many systematic points, a waypoint was collected every 4 paces in the vertical direction. For collecting fewer systematic points, a waypoint was collected every 8 paces in the vertical direction. In order to keep the intervals the same, the 2 systematic data collectors walked side by side, horizontally offset by pace, and with equal steps. The second method was random, in which data was collected in scattered intervals across the selected area. No specific pattern was used to collect these points. Both of the random data collectors stayed in close proximity to each other to ensure similar representation of the park. These points were taken at random distances from each other and followed no specific order around the park. Due to the fact that the points were taken at random locations varying in distance apart, parts of the park were covered more heavily than other parts. After the points were collected at Wolfpen Creek, the systematic mini, systematic view, random mini, and random view were exported to CSV files. These CSV files were used in ArcMap to create the models shown in the results. The models were compared to each other to determine the most effective way to survey topography using only a handheld GPS device.
These are some of the general results that the team was able to observe after analysis of the data. First, both in situ techniques trumped the lab technique in generating an accurate visualization of elevation. Second, the systematic approach for collecting in situ data appears more accurate than a random approach. And lastly, the number of points collected in the field for the purpose of surveying elevation does not seem to make an impactful difference. In the following slides, you'll be exposed to some images and figures that will help bring these results together. On the left, you'll notice a digital elevation model, and on the right, you'll notice an image of the surveyed area. This digital elevation model was created by using points from Google Earth. Just to give you some context, if you follow my cursor, this black area on the model roughly correlates to this area on the terrain. Furthermore, this side area on the model correlates to this area on the terrain. And this bottom portion of the digital elevation model roughly denotes this hilly area with the 4 lined trees. Also, by following the scale provided here, high elevation values, which are about 94 feet, are characterized by this white color, while low elevation values, which are about 77 feet, are black. So the darker the color, the lower the elevation, and the wider the color, the higher the elevation. As you can see, this DEM generalizes the elevation of Wolf Pen Creek, saying that the majority of the park falls within the same elevation. If we know this part of the model correlates to this geographic area, it's obvious to tell that this area is at a higher elevation than this area. However, on the model, this area, which should be at a higher elevation, so it should have a wider color, is the same as the rest of the park. Google Earth seems to capture areas of high elevation change, but small fine elevation changes cannot be captured using Google Earth. This next slide shows the digital elevation models generated when using a random data collection method. The top image is the random with many points, and the bottom image is random with few points. Both are extremely similar, and besides very fine details, differences cannot be discerned. Overall, this DEM did a better job of creating an accurate elevation profile of the target area than the Google Earth method. However, it is not perfect. To provide some more context, this area of the model, again, correlates to this area. And this bottom portion correlates roughly to this area. Also, the scale has remained the same, so white is high elevation and black is low elevation. This portion of the DEM is approximately this portion of the geographic area. As you can see in the elevation model, this is an area of low elevation surrounded by areas of higher elevation. If this was accurate, it should be a ditch of some sort, but no ditch exists in this geographic area. Furthermore, this patch correlates to around this area. This white patch relates to an area of high elevation, yet no hill exists in the remotely sensed image. The main issue with the random method is that it creates abrupt changes in elevation that are not accurate, such as the ditch that does not exist, and the hill that does not seem to exist. Finally, the last result slide features the digital elevation model created using a systematic approach. The top image is a systematic approach with many points, while the lower image is a systematic approach with few points. Although both are very similar, the many points image creates a smoother DEM with less noise. Out of all the methods, this method creates the most accurate elevation survey of the target area. As you can see by following my cursor, it starts with the low elevation area, and as you move up, the color starts to become lighter. Dark, lighter, which means the elevation is increasing as you travel up, which is how the terrain actually is. It starts in the low area, and as you move up the park, it gradually increases, low and higher as you go up. Furthermore, it accurately models terrain features in the area of interest, such as slight hills. If you focus on this area, you'll see it's a light gray color, but followed by a white area, and then followed by another gray area. This portion is this slope right here on the terrain. As you can see, just like the digital elevation model, it starts out at a lower elevation, and then is a high elevation, and then back to a low elevation, which is depicted again by this light gray, which is a low elevation, a white value, which is a high elevation, and then another low value, a gray value, which is a low elevation. Not only did this method produce the smoothest model, but it also accurately depicted the elevation of the target area with a moderate level of detail.
This study focused on answering the question of whether it is possible to accurately survey elevation without collecting in-situ data. In this case, are online systems such as Google Earth able to provide an accurate representation of an area as compared to in-situ data collected from the Garmin GPS units? Data was collected from each method and then composed into an elevation model. Based on the results, the DEM created from many systematic points from the Garmin provided the most accurate portrayal of the Wolfpen Creek Park. This is shown by how the DEM shows the most similar changes in elevation relative to the actual topography of the park. The DEM created from data extracted from Google Earth was the most inaccurate representation, being very flat with drastic elevation changes in some areas. Based on this research, technological lab data is incomparable to in-situ data and is not a reliable nor accurate representation of the actual Earth.